Hello, class 12th physics, wave optics, important question. How does the fringe width of interference change when whole apparatus is kept in a liquid of refractive index 1.33? So, we know that fringe width beta when placed in a medium is 1 by eta times that when placed in air. So it will decrease by 1 by 1.33 times that of fringe width in air. Okay, how it has come, then you can explain it by the formula beta equal to d lambda over d. Now, if when it is placed in air, so when it is placed in some medium, this lambda will change. Now it is lambda m, you can say, by d. And if we divide both of them, then beta m upon beta a, that will be equal to lambda m by lambda in air. And we know the refractive index eta is c by v, that is nu lambda upon nu lambda m. Nu will remain same, frequency will remain same. So lambda by lambda m is eta, that is refractive index. Some people write it mu, so don't get confused. It is mu also. Some people write it n, so I'm using the symbol eta, so don't get confused. So eta equal to v lambda by lambda m, that is lambda in vacuum or lambda in air. So here it is lambda m by lambda a, so it means it is 1 by eta. So that is why beta in medium is 1 by eta times that of beta in air. You can directly write this, or through this entire explanation you can come here. How angular separation of interference fringe actually angular width of interference fringe change in young double slit experiment if distance between the slits is increased. So what is actually asked here, angular separation. So it is something theta, but we will not use theta as that theta is used to express that angle. Why it was used in derivation. Phi we can't use because it is used generally to express phase difference. So we will use angle alpha. And what is this angle is all about? So if we have this interference pattern, this is the central fringe, and okay, so these are two consecutive fringes, and if we want to find distance between them, that will be fringe width beta, and now this is the angle alpha, and almost the distance between the line joining slit and the screen is d. Actually this is not the slit, slit will be somewhere here, and interference pattern is so formed. It is just a line drawn from the middle of it. So if you could remember, then we have marked this point as C. You can see the derivation part in my earlier video. So this is beta, this is d. So we can say angle equal to arc upon radius. So we can say alpha equal to beta upon d, and beta we know d lambda over d by d. So alpha is lambda by d. Now the question is how angular separation between interference fringe change if the distance between slits is increased. Distance between slits means small d. So if d is increased, then alpha will decrease. Okay, now state why two independent sources of light cannot be considered as coherent sources. So to qualify the condition of coherent sources, the sources must be must have same amplitude, same frequency, and they must have constant phase difference. So the okay, the correct answer will be two identical sources, two independent sources. Actually they haven't said identical. So two independent sources must fulfill full हो गया ये तो. The condition of coherent sources. That is same amplitude, same frequency, and constant phase difference of emitted waves. First two conditions can be mechanically fulfilled, but at which instant which electron will make transition so that light will be emitted is a matter of chance. Which can't be controlled. So phase difference cannot be kept constant. So that's all. Two independent sources of light cannot be considered as coherent sources. So the idea is they emit light, and the emission of light depends upon electron transition. For more details, atom chapter is there. You can go through it, or in my video on this interference, entire optics actually, I will put its link in the description. You can go and check it. Alright, what type of wavefront emerge from point source, distant source? So from point source, spherical wavefront, and from distant source, plane wavefront. We can draw also. It is not required, but we can do it. That's all. Draw some waves. And distant source, so from distant source these parallel lines come, and you can see, if you are not good at drawing, you can do this thing, or if you are good in drawing, you can draw this 3D diagram. These are the waves. They didn't ask to draw, they have just asked, so you can put their name and that's all. But if it is asked to draw, then you have to draw it. So more drawing, draw a diagram to show refraction of plane wavefront from. So how will it refract? Actually, complete theory is there. In fact, using this diagram, you can even explain it if its explanation is asked. So this is the plane wavefront. We can show three rays here. Okay, so 3 points actually, 3 points are there, and from these 3 points now secondary wave will emerge out. So from this point, because it will travel less distance in denser medium, it will spread more. So we can draw a big circle here, and here it will travel through denser medium for same amount of time. It will travel lesser distance, and it will also travel more distance. So if we draw a common tangent, so this will be the wavefront, refracted wavefront. And if we draw waves normal to its surface, so their center will be the focus of this lens. So this is incident wavefront, this is refracted wavefront. Now in the same way for concave lens. Okay, so once again here we have a plane wavefront. Actually these lines are not required, but due to custom I'm doing it. Now what will happen, this will have to travel less distance in this denser medium, so it will spread more. So we can draw it like this, and from here it will spread less. It will also spread less. So this will be the refracted wavefront. And now this is how waves are now perpendicular. So center of this wavefront will be here, and it will called its focus. And prism, actually triangular prism. Prism itself is a general name. It can be of any shape, so they must say a triangular prism. So this is the incident wavefront, plane wavefront it is. So this point will travel more distance, it will spread in a big amount. So let's draw. Oh, in fact I have to draw somewhere here, so I'm doing it. Just ignore this. Now this one. Okay, and from here it will spread through lesser distance. See, I can make it somewhere here also, but that will create a mess, so that is why I'm drawing it here. So it will spread in more region, and in the same time it will spread in lesser region. So this will be the refracted wavefront, and this is what happens if we follow it somewhere here. So this is what happens. Parallel to it there will be another. So this is how it will emerge out. In fact you can draw a bigger arc here and a smaller arc here. So in fact it will be retained in this manner. Next, draw a diagram to show reflection of plane wavefront from convex mirror. So here we have convex mirror. So again an incident wavefront, and from here it will spread all over, but it can't go this way, so now it will move that way. So also it will also spread, but we will consider those waves which emerged out after striking this point. So those rays which reach here and then spread out, they will take some time. Actually in the meanwhile it has spread this way, but it will go here and then start spreading, so it will spread in a smaller region. It will also spread in a smaller region. So a common tangent, this is a reflected wavefront. And the center of this will lie at the focus of this convex mirror. In the same way we have this concave mirror. Actually we should not over arc this. Okay, so this is the plane wavefront. Now from here secondary wave emerged out in a bigger region, it will also, and from here it will in the meanwhile spread in a smaller region. In fact I will just show it this way. And now a common tangent, this is the refracted wavefront. So it is somewhere here, it is focus. Alright, so next is differentiate between a ray and a wavefront. So ray, it shows the path of light, followed or to be followed, followed. That's it. And wavefront, okay, so here I'm writing its definition. The surface drawn normal to the, oh, normal, in fact, normal to the direction of propagation of wave at each point of which there is same phase. And now last one is, how would, okay, the basic idea for wavefront is, we are not dealing with a single wave like here we generally use with single ray we can use, but here a well-defined number of waves should be there, and they must be in same phase, means all the waves must be in same phase in order to explain whatever be the condition going on with respect to that wave. So instead of studying single wave, we study a group of wave, and that must be in same phase. How would the angular separation of interference fringe, angular separation again alpha as we did earlier, change when distance between slits and screen is doubled? So earlier it was only distance between slits, which we can say slit separation, but here distance between slits and screen means distance between slits and screen. They are talking about this. The confusion part is here when they talk about distance between them, so they will say distance between the slits, and when they ask about this distance, they say distance between the slits and the screen. So it looks like they are giving two condition, but it is not that. It is distance between slits and screen means this distance. So we know earlier we did it, so right now I'm directly using that expression alpha equal to lambda by d, which is independent, of d, so no effect effect nahi. How does fringe width in young double slit experiment change when distance between slits increase? So fringe width, formula for fringe width is d lambda over d. Distance between slits means d is increased, so v is inversely proportional to d. So if d is increased, beta will decrease. And here is a confusion. How does fringe width in double slit experiment change when distance between slits and screen is increased? So here don't get confused with this. Distance between slits is small d, and distance between slits and screen is capital D. So b is directly proportional to d. So if d is increased, then beta is also increased. How does the fringe width in young double slit experiment change when blue light is replaced with red light? So we know that wavelength of red is greater than wavelength of blue, and beta equal to d lambda over d, that is beta is directly proportional to lambda. So we know lambda red is greater than lambda b, so beta for red is also greater than beta for blue. So if it is replaced with red, then beta will increase. So here is the question which is not directly covered in the discussion in the video, the explainer video, in which I have explained this young double slit experiment. In a single slit diffraction experiment, okay, this is about diffraction, slit width is reduced to half. Still this is also not discussed there, so it is covered here in the question. How would this affect the size and intensity of central maxima? So we know half linear width, in fact full linear width we can say, width of central maxima is twice d lambda over d. Actually half linear width is d lambda over d, which can be directly derived, and for both sides it will be full width, which is twice of d lambda over d. Here this d is important, it is the slit width. So if it is reduced to half, so if d is reduced to half, we can solve it. We can directly put the answer ki if d is reduced to half, then width of central maxima will be doubled. Or we can do it in this way also. Width of central maxima, I'm writing it w. Actually generally I write it y, but y is I refer for half linear width, so that is why I'm using w. So w1 is 2d lambda over d, and in case 2, when slit width halved, so it will be 2d lambda over d by 2, that is twice of 2d lambda over d, which is same as w1, so twice of w1. So same here we can say if d is reduced, so you can write straight away, or you can go through this way. But second part, intensity of central maxima. Here what happens, if we reduce the size, then intensity would also reduce. So we can directly say that intensity, in fact I will write here separately so that you could easily understand. Okay, so intensity, see if light is coming from narrower region, little smaller region, then intensity of light would also reduce, so intensity will decrease. Here you can also answer this thing in a different way, like intensity is proportional to the size. Actually there is not a direct relation for that, but the size of aperture. And and its square, that is slit width square. So if it is reduced to half, then intensity will become 1/4. Now, well, this type of explanation is not completely covered in the syllabus, so we can ignore that part, but still this is also the way to answer. So if it is halved, then intensity will be 1/4, because d is reduced to half that way. So but directly you can say intensity will decrease. Define the term coherent sources. So two sources, two or more sources which emit wave actually, but here we are talking about optical interference, so which emit light having same amplitude. Actually you can write nearly same amplitude, same frequency, and constant phase difference. Define wavefront. So earlier I have defined it in other question, so I'm not covering it here. But remember, in that question, two definition you have to write, and marks would be 1 mark question only, and this is also 1 mark question. So this thing happens sometime. Sometime you have to write same amount of answer, and they mark it as 1 mark or half mark. So it is up to the person who set the paper. Okay, state one feature by which the phenomena of interference can be distinguished from diffraction. State one phenomenon. Okay, so one phenomenon, one feature, we can write many of them. So actually they want to ask about the distinction between them. So first thing, interference pattern consists fringes of same intensity. whereas diffraction fringes has decreasing intensity. One more, they have asked for one feature, but we can um, explain more about it. We can write more about it. And second one is intensity of central bright fringe is same as rest of the fringes. In interference, intensity of central bright fringe is maximum in diffraction. Another interference pattern has greater contrast between bright and dark fringes. In what way diffraction from each slit related to interference pattern in double slit experiment? So in double slit experiment there are two slits. We can say that if we close one of them, then interference pattern will converted into diffraction pattern. So we can also say that interference is the superposition of two diffraction patterns. So how we can say that? So first point is intensity of minimum of diffraction pattern is not zero, whereas intensity of minimum of interference is zero. So in this way both are related to each other. Second thing, intensity of all the maximas of diffraction pattern is not same, whereas intensity of all the maxima of interference I generally write IF is same. So this is how. So superposition of two slits, diffraction, or we can say modulation of, mixing of, modulation, diffraction results in interference pattern. When tiny circular obstacle is placed in the path of light from distant source, what is observed and why? So the answer is if this is the way of light and we put a small obstacle here, very small, tiny one, then it must create a shadow here, but instead of creating a shadow, it gives a bright spot in the middle surrounded by that pattern, once again diffraction pattern. But the most important part is central part is a bright spot. So what is observed? A bright spot is observed at the center because of diffraction. All the waves coming to the center interfere constructively. In the same way, sometimes they ask why central maxima is bright. So the same reason is there. All the waves coming at the center interfere constructively. In young double slit experiment, two slits this much apart. So this is slit width 0.15 into 10 to the power minus 3 meter. Wavelength is this nanometer. Find distance of second bright fringe. So we need to find y2 bright. So we know the formula n d lambda over d for bright fringes. So here it is 2 for bright fringe, second bright fringe, the 2, and oh, I think something is missing in this question. I have missed it. So let us suppose d is actually I think I have written half of the question. So for the sake of simplicity, I am taking 1 meter d, distance between slits and the screen. So lambda is 450. Okay, sometime if this kind of half question comes in the exam, then okay, you can put the formula and you will get the bonus marks. 0.15 into 10 to the power minus 3. So it is minus 6, and if we shift zeros, it will be 2 into 4, 5, 0, 2 more zeros, 15 into 10 to the power minus 6, and so it is 6 into 10 to the power minus 3, or we can say 6 mm. Due to diffraction, we can able to hear sound even if obstacle is large. But okay, so the thing is, if there is some source of sound, and here we are standing, so still sound uh, reaches us by diffraction. But same thing not happens with the light. Let us suppose this is a torch and we place an obstacle here, so we don't see, actually, if I'm not talking about the diffuse light, but if it is a straight light, focused light, so it will not go like this. So then how can we say light shows diffraction? So for diffraction to take place, size of obstacle must be of the order of wavelength. So wavelength of sound is large. So diffraction in sound can be easily observed. But wavelength of light is very small. So obstacle of same order will produce observable diffraction. That is, if obstacle has width or size of the order of 10 to the power minus 5 to 10 to the power minus 6, even less than that, then diffraction of light can be observed, but not with meter, not with other type of obstacle. In young double slit experiment, what is the condition to see interference clearly? So it is S by S. Actually, this is the thing you have to learn, memorize, mug up. This is the condition for that setup. So in that setup, there is a point source, first slit, and there are two slits placed in front of it. So this slit, the width of this slit is given by small s, and the distance between this slit and these slits is given by capital S. So small s is slit width, source slit width, which is also important, upon distance between source slit and double slit. Draw the shapes of fringes in young double slit experiment for point shape slits and line shape slits. So for point shape slits, shape looks like this. Hyperbolic. And for line shape slits, these are straight, like this. And in the same way, we have another question. Draw the shape of fringes in single slit diffraction for circular or point and linear aperture. For circular, it will look like this, and so on, with decreasing intensity. We can't show that with decreasing intensity as we go away. And with linear aperture, this central maxima, and then minima, then maxima, with decreasing intensity, and so on.